Okay. Do you need me to go over the first one? Do you need me to explain what I'm asking? Does this one make sense? All right. Yeah, just go look in the TCP header and look in the IP header and find examples of 16, 32, 40-bit. But this one is even simpler than that. You really don't even have to look those things up. So there's only one address we've looked at that's got 48 bits. Do you guys know what it is? Yeah, the hardware address. And then what address do we use all the time that's got 32 bits? Right, your IP address. Makes sense? There's others, but that's one. What about a 16-bit address? Yeah, there's several of those. So you can go hunting. Partly this is a trick to get you to go look at the headers. It's a sneaky trick. Yeah, that's an address, right? So just work your way up the stack. 48, 32, 16. It's kind of interesting that they get smaller as you go up. There's sort of a message in there. Counters, if you add counters to that and links, then those are different types of addresses that we've looked at. What's a 32-bit counter that we've seen? And it's in TCP, I can tell you. You want me to pull up the TCP header? Yep, that'll help. That won't work. It'll have to open Excel, which is super slow. Has anybody heard any more on when Apple's going to come out with the new laptops? I'm going to ask this every week. You know. And then when you hear it announced, you guys will all know that I know what Profe did today. He ordered one. That'll be the first thing I'm going to do. Okay, here is the TCP header. Do you see any 32-bit counters in here? Well, not when I zoom it back and forth. Let's try this again here. And the sequence number going one direction, the acknowledgement number coming back the other. So that's a big range of sequence numbers. Ay, perdón. Gracias. Okay, what was the next one here? No, this one. We also had one in here for a couple of the others. Those are mostly in the IP header. So we can open that one up too. No, there we go. So anybody see a 4-bit length? Yeah, right up here. So just kind of go through and find some of these things. Like, this is obviously a length that says length. The identification number is not a length. It's like a serial number. Time to live, is that a counter? Yes. Protocol, which protocol number it is, that's not a counter. The checksum isn't really, that's a calculation. The fragment offset, that's a length, isn't it? How far in are we starting this packet? The IP addresses are neither lengths nor counters. Type of service is neither one. These are flags. Those don't really mean anything. So you can kind of, yeah. Absolutely, why not? It says length even right here in the name. It's one of the choices. There's not just one answer to some of these. I just want you guys to kind of be familiar with what the header looks like. All right? It carries most of the stuff you do. Have a little respect. Okay, suppose we use an address space with only 4 symbols. 5 symbols. 0, 1, 2, 3, and 4. So when you write down, say, a sequence number, it's going to be 10 digits wide, and each digit has to be one of these 5 symbols. So it's kind of like a base 5 number, I guess. So how many different combinations are there when you have a 10-digit number, and each digit has to be one of 5 values? 4 10 to the 5. Well, which is it? You tell me.
I think it's 5 to the 10.
Okay, why?
Because you have 5 different possibilities.
Right.
And different.
Okay, so can anybody argue the other way around? Is everybody like clear? Do they agree? Permutation? Exactly, right? I would use that analogy exactly. I would remember that when we're talking about binary, it's like 2 to the 32nd IP addresses. So it must be the base first, and then the number of digits is the power. So just use something you already know. It's hard to do it in decimal because it'd be 10 to the 10th, and that doesn't really help you a lot. So base 10, all because we have 10 fingers. And you know that 11 digits is a dominant DNA trait. I have a niece by marriage, not by blood. I just want to point that out before you guys start any jokes. I have a niece by marriage who has 11 toes. And it's a dominant characteristic. Her children will have 11 toes, likely. So just be glad that didn't happen sooner, or we would all be counting in base 11 instead of base 10. Who couldn't use an extra finger now and then, right? Yeah. So one of the radio programs I love to listen to has a news program every afternoon. And one year they had a contest. Said if you could change one thing on your body to make it more useful, what would it be? And I still remember the host saying, there are a great number of suggestions that are not suitable to be aired on the radio. Thank you not at all for sending those in. But one of the ones I remember that was really good is an eyeball on the end of one of your fingers. So you could peek around the corner and look under the couch and like see what's in your pocket or look down in your bag. Isn't that great? Be like E.T. or something. So anyway, okay, so I like that analogy. That's how I would remember that as well. Okay, and the third one, do you guys understand the third one? It's something you can do with a little work. That's different than I haven't looked at it yet. You know, I haven't looked at it is not the same thing as I looked at it, and I don't understand at all what you're asking. So, which ones were you confused by? Only numbers 3 through 9 or something like that? Yeah.
I was confused later on.
Okay, so let's take a quick peek and make sure we all kind of know how to do these. This is a /19 network. All I'm asking you to do is, here's your network address in binary, here's the subnet mask in binary, all right, and you've got a few functions like and, or, and not. What would you apply to one or both of these things to, for example, get the number of IP addresses available? You know, you can basically mask this thing off, you can knot this and turn it into zeros and then ones, and then or it with this thing or and it with this thing, and clear off everything except the host addresses. There's one down here that says the network number. How are you going to get the network number? Well, the network number is just the part up into the slash, right? And everything else after that is 0. So just and these two things together. You can see that right there. And them together, and it'll force all these to be zeros, and it will leave these alone. That's exactly what you want for network number. Count up the first 19 bits, leave them alone, 0 out the rest. So things like that. That one should be easy. Text me if you get stuck on that. Here's another one in here, a strange sequence of contiguous IP addresses. So here's the way to do this one. This is back to base 256, which we went over one day. And you're counting in base 256. So if I give you a big number and I tell you I want to, let me move this over and give us a new little chart here. There we go. If I give you some number, you know, something with some digits in it, and you've got certain fields in here, you're going to figure out how many in the most significant digit can you get in there first. Like, does this number go up to the 10,000s? And you'll take those out. Whatever's remaining, you will see what you can put in here. Whatever's remaining, you can see what you'll put in here. So base 256 will work the same way. I have this big number, 50,595,078, and I'm told that starting at this address, I have this many more after this first one. Now I said after this first one so you don't have to subtract 1 at the end. Otherwise, if I told you you started at .0 and you had 200 addresses, the last one would be 199. So you'd have to take 200 and subtract 1. I don't want you to have to do that. I just want you to add this number. So I'm asking you to add 50,595,078 addresses on top of this one. How can you do it? It's base 256 math. So the first thing you want to do is try dividing it by your most significant digit. Divide it by 256 cubed and see what you get. Take the whole number out. Let's say it goes in here, I don't know, 2 times. And then it's going to have, 2.13214. It's not going to be an even multiple of 256 cubed. But you can get a couple of them. They're so subtract it out. Once you figure out how many will go, then take this number and subtract out 2 times 256 cubed. What will that leave you with? The remainder. The remainder's got to fit in the last 3 digits. We move on to the next digit. We try dividing whatever the remainder is by 256 squared. Take out however many whole ones of those are left, subtract it from what's left, and you come up with another remainder. And that has to fit here. You try dividing that by 256 to the 1, and whatever's left is left. So you'll convert it to an IP address that way. You can find a website to do it. You can write a spreadsheet to do it. But if you get one on the exam, you need to know how to do it. All right? So divide by the positional value. If this was dollars, this would be ones, tens, hundreds, and $1,000. Or pesos, ones, tens, hundreds, 1,000 pesos. So first you figure out how many 1,000 peso notes it would be. Once you've converted it into IP, you write the number down here, and you add it up. And you just watch for carryout. So this one's very, very close to the largest allowed number, which in base 256 is 255. I know now you're not asking the question. I'm not even going to. I know you now, right? I've got practice. You've trained me. So 255, we're very close to it. So if I go over, I'm going to have to carry 1 out. All right? All right, that's not hard, but takes a little practice. Okay, fixed length subnetting. So does this one was this one of the ones you got confused on? Or were you okay on this? Was this one okay? Number 5, the fixed length subnetting one? All right, so I'll do it briefly then for everyone else. So, okay, let's, yeah, okay. I changed that one up, so there's a risk that I screwed it up. So we'll take a look at that. So in fixed link subnetting, you've inherited a network with a network mask of n. So there's n bits that you cannot change. You've been given a network. You can play with all of the rest. You can set them all zeros, all the way up to all ones, and you will have 2 to the 32 minus n possibilities. So far, so good. Normally, that's like the first step. When somebody gives you a network, they're going to tell you what n is. They're going to tell you it's a /20, or it's a /25. That's n. So that's what it means to be a /n network. Okay, so what you're now told is, before you start handing these out, we want you to divide them up into groups. So you're going to start here. You can't do anything to change the first n bits, but you can change the n+1 bit and the n+2 bit and so forth. So the first thing is, you need to divide it into 2 groups. How many bits is that going to require?
1.
1 bit. It just requires 1 bit to do it. So you're going to give each of them a /n+2, and you will use n+1 bit as your one that you alternate. So half of them are going to have a 0 that starts with a 0. The other half are going to have addresses that start with a 1 for the n+1 bit. The first n bits are shared. Those don't change. The n+1 bit is a 0 for one half, a 1 for the other half, and they have 2 to the n-2. That's not true. 2 to the 32 minus n-2 bits left. I never really know what N is. I never find out. Okay. And if you need 100 subnets?
7.
7. Why 7?
Because 2 to the 7 is like 100.
Yeah. So the brute force way to do it, if you do it on a calculator, is say log base 2 of 100 is going to give you 6 point something greater than 0. So you must round it up, because you can't have 6 point something bits, you need 7 bits. In fact, it'll be like 6.85, something like that. I actually had a friend in high school, his name was Bob Scholl, who could do that in his head. You could tell him, okay, Bob, log base 200. People flew in to test it from like university. They didn't believe it. He also could do square roots in his head. Like, what's the square root of 27? And he'd go, he'd just start blurting it out. He'd be slow. He'd like 6.32. But I'm like, what? So, can any of you guys do that? Am I the only one? Okay, good. Just want to make sure. All right, so what part E does is it works it backwards. What this one is basically saying is you need to allocate subnets that have a certain number of addresses. And therefore, you're going to have to use powers of 2, because your subnets are going to have 2, 4, 8, 16, 32, 64 addresses, because that's basically how we do it. And you notice that M is less than 2 to the 32 minus N, so there's no conflict. You're not going to have, like, you've been given a /10 network and somebody goes, well, I need 2 to the 25th numbers. Well, you're not going to get that with the /10. Too bad. We're not going to have that problem. We will not conflict with each other. So what I want you to help me figure out in this one is what's the equation for how many subnets you can actually allocate. So if I gave you a table, I actually calculated the entire table, but it was too big. Maybe this will help you kind of check to make sure you are going on the right answer. So if I tell you you have a /20 network, all right, a /20 network, there's 12 bits left, right? If you have a /20 network, 20 bits, there's 32 minus 20 equal 12 bits left for the hosts. We all agree on that? Out of that 12 bits, and I'm going to highlight this row here, how many addresses do you need in each subnet? This is the opposite question. Instead of me telling you how many subnets I need, I'm telling you how many addresses I need in each subnet. So if I tell you I need 16 addresses in each subnet, then that means you can have 256. Here's why. To have 16 addresses needs 4 bits. So I'm going to have 4 bits down here. You got to leave me with 4. So out of the 12, there's 8 here. 2 to the 8th is 256. That's why that number is 256. So the equation is going to be something like start with 2 to the something. We know we're going to be raising 2 to the power of something, because that's how I'm going to tell how many. I'm trying to figure out how many bits are left. So I take my N that I've got. I'm going to need to put in here something that has to do with log base 2 of however many addresses you gave me. And that's going to give me another number of bits, M, let's say. And figure out, you're going to have an M in here, you're going to have an N in here, you're probably going to have a 32 in this equation. And you're going to tell me how many subnets I can have based on that. So this is basically, again, saying, I give you a /8. That one's too big. Let me give you a different one. I give you a /12, and I tell you each one of the subnets needs to have 1,024 addresses in it. I ask you, can you pull that off for me? You go, yeah, I can give you lots of subnets with 1,024 addresses. And I say, with the /12, you go, yeah, with the /12. Well, how many can you give me? I look in the table, and I say 1024. Why? Because I started off with 32 bits. You took 10 of them away from me. That left 22 bits left. And is that right? No, I started with 12. So /12, thank you. That leaves 20 bits left. You need each one to have 1,024 addresses. How many bits does that require? Yeah, 10. I heard it from someone. So what's left is this. This is what I want the equation for, is that value. Make sense? All right. That should take you 2 minutes. And if it's taking you more than 15, get on the text chat and ask, like, what's the secret? Right? Learn it, don't kill yourself over it. You want to make progress in this. Okay, telephone company wants to obtain a block of addresses to support 100,000 subscribers. They are leased on an annual basis. What I'm basically asking you to do is go to the table that I gave you in the homework folder, where I put all of LACNIC's prices. It was a pain to find them, so I don't want you to waste a bunch of time doing that. I wasted my time, and I'm like, multiply that by 100? I don't think so. I don't need 100 students coming to do this. So I gave you the prices. I just want you to figure out what it's going to cost. You have to be a little bit careful, because these are the addresses that go from Telmex's central office to your house. So what do we remember about that? When I have a network where I have one router in the middle and I have all these subscribers, what do they all have in their houses? What do they come and install in your house when the little white Telmex truck shows up? They give you a laptop? A router. All right, very good. So how do these routers connect to each other at the IP layer? Can they send traffic to each other? Hope so. If not, you don't have a network. So therefore, these devices are on the same what?
Network.
Network, LAN, subnet. Is there anything else on that subnet? Do you want anyone else to see your traffic? No. So you probably want to be the only one on the subnet with this router port. Am I right? That would be nice and secure. All right, so let's talk about this subnet. How many addresses does this subnet need to have? How many devices are on the subnet? Yeah, but forget that. I'm only talking about you. You're special. You're like not 100,000 people. You are one person. So how many? Well, but if you have a subnet with only one device, who's it going to talk to?
You have.
Takes two to have a conversation. Takes two to tango, right? Keep going. Uh-huh. At Telmex. Yep, at the central office. And this is you. So I heard somebody over here, I think, say it. You need 2 addresses. Remember, all router ports have addresses. That's why I don't like the way they draw the diagram in our book. They try to draw it away like near the switch. It's not on the switch. The address belongs to the router port. Every cable that plugs into the router, every one of them has an IP address. Different. Every one is a different LAN. So think about 100,000 cables plugging into some big, giant, massive array of switch ports, and they have ways of not making it 100,000 cables, but it's logically is exactly what it is. Okay, so back to this subnet. This is a subnet with me and you, Telmex and you out here. So that's 2 addresses, right? So is that a /31? Because that just leaves 1 bit left, and it can be a 1 or a 0, and I give you the .1 and I give me the .0. Is that enough for a network? What else does a subnet need to have?
Get broadcast.
Just have a broadcast address. The broadcast address is you take all of your host bits and turn them into 1s. Well, that's a problem because I've already signed the one and only host bit I have to this. So that won't work. I need more addresses, right? What's the next step up from here? /30. Now I have 2 bits. So I have how many combinations of bits now?
4.
4. I have 00, 01, 10, and 11. How about I give you this one and I give me this one? We use this one for broadcast and we use this one for the network number. So you can put in a routing table. Do you think that would work?
Yes.
This is exactly what ISPs do. That's why they eat IP addresses like candy. They use millions and millions and millions of them. All right, so now you know how big each subnet needs to be. You can go back to the table, figure out how many of these you need to go buy, and see what it's going to cost you. Okay. Number 7, variable length subnet masks. All I want you to do with this one is go to Light Mesh and try and figure it out. Has anybody played with Light Mesh yet? Do you think you can pull it off?
No.
Nope. All right, you want to play with one? Let's do one here. All right. So let's suppose I'm going to do something similar. I'm not going to do exactly the same answers, okay? So let's say we have a network that is a slash, I don't know, a 12. So we got a bunch of hosts. And there's 4 groups, A, B, C, and D. We'll keep that part the same. Group A, let's say they need 20,000 hosts. So I see a 16 here, and I see a 32 here. So I'm going to pick the 32 and drag it over here. There's a lot of room in this network. 32,000 hosts only used one of these little blocks. That's like amazing. Okay, so that's group A. Maybe I should make this a little bit smaller network. Let's make it, that looks a little better. Let's say they need 10,000 addresses. Right, so they're going to have a /18. So they've used 10,000 so far. There's group B. They have a number that's not very much smaller, but it's a little bit smaller. Let's say it's 7,000 addresses. So they don't need a /18. They'll fit in a /19. So I'll come and drop them. Where should I put them on here? Should I put them adjacent or not? Well, in the problem I tell you, B is going to be combined with A later this year. And it would be nice if you didn't have to re-address everybody when that happens. Well, I know how to do that. I'll just put them right next to A to start with. Later on in the year when they combine, I'll just rubber band this out and make it a big giant /17. So it will include this, it will include this, and you'll have some blank space over here that you won't use right now for another one. So this one will be blank. So this will be A and B and blank. So you'll do something like that. Then you've got group C. They've got a handful of locations. Let's say they need 4,000. And you've got group D, same thing for them. So I'll do, you know, something like, maybe something like this for these guys. And that's it. So then I ask you, could you have gotten by with a smaller network? Like if this was a /17, would it have worked? No. A 17 is only enough to get this, this, and this. You would never have been able to do the last 2 groups, C and D. Okay, what about how much am I wasting? One thing that some of these problems will ask you is calculate how many of these things are you giving out. So all I'm asking is once you get the design kind of like you want, take a picture of this, just this much, and then open the table. I want you to label what these things are for. So you'll say group A, and you'll say like group B, and then this one would be, you know, maybe extra growth for group A and B, or reserve for A and B, or whatever you want to call it. Give it a name like that. This would be like group C, and this would be like group D. And that's it. Then you hide and re-display your table. Now it's got the names. I want you to paste this into your homework as well. That's it. All right, so just play around with building these things out. The things I'm going to be looking for is if I tell you 2 groups are going to join, don't separate the IPs. Put them next to each other. They're telling you they're going to join each other later this year. And if you have group C, don't put it in the same block as A and B unless they're going to have something to do with each other. So something simple like that. Okay, then we have fragmentation. What is the relationship between the size of the fragment offset field and the fact that a fragment must be a multiple of 8 bytes in length? Explain to me what it is about the fragment offset field that requires that my fragments be multiples of 8 bytes. We talked about it extensively. We gave other examples with this 4-bit version, 13-bit version. We talked about why the 16-bit version doesn't need it. So just remember, in general, if I don't have as many bits as I want, that's okay. I can stuff it in the end. Here's an answer that every American student will know, a question that every American student will know the answer to, and it may be the same for you guys. When it's the end of April or middle of April and it's time for you to turn in your income tax return to the Internal Revenue Service, you have a form from everybody you've worked for, from all of your banks, and they all tell you exactly how many dollars and cents you earned, you paid, you got an interest, whatever it is. But the IRS doesn't want that much detail. They only want dollars. They don't want to know about the cents. So you would normally, if it's, say, you would normally expect to have room for up to $9,999.99. Is that, if that's all the tax return let you put down? That's 1, 2, 3, 4, 5, 6 digits that you need. They're telling you now, we're only going to give you 4 digits. So we're going to make the last 2 zeros. We're going to force you to make the last 2 zeros, which is exactly what they're doing. They're not going to let you put down centavos. They only want to know whole pesos. Right? So that's exactly what's going on with fragment offset. You didn't have enough bits, so I stole some away. This number is smaller than this one, so we're going to force some of the bits over here to be zeros. Right? So see if you can explain. You can Google that as well and learn it from that. Okay, here's a little Wireshark trace. I ask you a few questions about what does this mean? What does it look like? The first part's easy. It gets a little trickier as it goes on. Flow and error control, you can glance through the book. It has the answers in black and white right in the book. And I think I put the PDF of the book in our folder. I think so. Does anybody, like, not? Okay. So it's there. I don't want to ask if anybody doesn't have the book because that might embarrass you. I don't want to embarrass you. Okay. Your answer should be, certainly I have the book. We've read it religiously. What are you talking about? That was always my answer. Yes, I read it twice, in fact. It was so interesting to me. Like, okay. There's a few questions in here on ICMP. That's also right out of Chapter 10. And I have destination unreachable, 16 codes defined. Which ones are for messages that can only be sent by host? If you find the magic paragraph in the book, it will tell you exactly the answer to this question. So I just want you to get some visual memory around what that table looks like, just to kind of reinforce types and codes. That would make me happy if you just took a hard look at that. And then what pair of ICM message types and codes are caused by running a successful trace route? By successful trace route, I mean one that doesn't come back with just rows and rows of asterisks, or one where you never reach the host at the end. A successful trace route is one where you get an answer from the router, and at least one, and you get an answer from the host. And if you don't know the answer to this, Wireshark it. Wireshark and look for ICMP. Filter for that. In the filter field in Wireshark, you can type in, just simple as that, ICMP. Hit return. You have to hit return. It'll turn green before you hit return, which is not good enough. Let me turn this off. I'm going to turn off Wi-Fi. It'll interrupt my audio for a minute. Okay, I think I'm back. So I'm just going to come up here and say ICMP, and I have to hit return. There are none yet. So if I come down to my terminal window and I say something like trace route to www.tech.mx, bam, I now have ICMP messages. And I don't know that this is going to finish, so I don't know that I like this one. Let's try a different one. Trace route, www.etesson.mx. That one worked, and I got all the way to the host at the end. So all you got to do is just open these up and look in here and figure out the type and code. They're shown right here. But there's a couple of different ones, so you need to kind of take a peek at it. So Wireshark's the easy way to do it. You also can look in the book and figure it out. It's like, it's got to be that one. Okay. The other chapter was chapter 9. That was on ARP. So if you find an ARP packet on your network that has the same value for sender and target protocol address, what do we call that type of ARP? If you run Wireshark long enough, you will see one of these. So we can try it. I'll just see if I see one. I'm more likely to see it on Wi-Fi than I am to see it on, oh, hold on. There's some audio issues here. Mute on entry. Okay, I think people figured it out. Sorry about that. I don't know if I'll see it on Ethernet, but let's try it. So I'm going to go up to my filter field, and I'm going to type in ARP and hit return. And I'm just going to wait and see if I see one. It's more likely on Wi-Fi because there's more stuff on Wi-Fi. Here's a broadcast from the router. So there's a whole bunch of ARPs here. If I pick one of these and I go down and look at the sender IP and the target IP, they are not the same. Okay, so that cannot be the answer to A. I'm looking for one where they're the same. And if I go through these, I notice they're all different. If I look down here at the bottom as I'm scrolling through, so maybe I need to go to a different interface. Maybe I need to capture on Wi-Fi instead. So you'll find one, and it will look very different than all the rest. You don't have to go poking through. All of these look the same to me. If one of them is not right, none of them are going to be right. It will look very different. It will say something different in the note, in the info. All right, so take a peek at that. And if you can't find it there, open up one of the PCAP files, and text me if you get stuck, you can't find it, and I'll throw a few more out there for you to open up with Wireshark. And you can search for ARP. The same filter will work, even though it's a pre-built file. You can still open it in Wireshark. You usually can just double-click on it. But if not, just open it from within Wireshark, type in ARP, hit return, and it will filter everything else out. So I have some ARP traces for you specifically that you can look through. So this is a little bit homework and a little bit lab, tiny touch of lab. Okay, in an ARP request, the value of the target hardware address is in the payload is all zeros. What is the value of the destination hardware address in the frame? Let's see, is that what I wanted to say? Oh yeah. So in the ARP payload, it's all zeros. What is it in the Ethernet frame that's wrapped around it? That's what I'm asking you. In the frame, not in the ARP packet, but in the frame. That should tell you Ethernet. So go find one that's got zeros in it and look to see what the address is at the Ethernet layer. ARP is at the ARP layer, one layer down, layer 3. I'm asking you, when you see that the target address is all zeros in layer 3, back up and what's the address at layer 2? It's always going to be the same. All right. Okay, and then I show you a little packet here, and I basically want you to fill this out. Fill out the ARP table based on what you see in here. Does that answer your questions? So this is not hard, in my opinion. What do you think? Yeah. Well, this homework covers 9 and 10 and I want to say 4 or 5, not the routing ones, but the IP address ones. There's like 4 chapters on IP. It'll be, I think, just those chapters, but if you don't strangle me, there's one other thing I want to walk through with you guys, and it's the homework that I really wanted to do with you today. So here's the deal. Let's spend 1 hour together, go through as much of this as we can. You will leave here with the answers, because we're going to do it together. And when the hour's up, that's as far as we're going to go. We'll just stop right there, and that'll be the limit between these other 2 and this one, what's going to be on the test. Deal? So Do you understand the concepts on the homework that we just went through? If you study it some more, do you think you can get your arms around it? So on the test, I will ask you a question to fill something like this in from a trace, from a Wireshark trace, or I may do it backwards. I may say, okay, here's your ARP packet, here's the blanks up here in this, fill in the blanks in the trace route, or sorry, in the Wireshark capture. It's just one versus the other. You can bring a cheat sheet with you, so you can make a copy of this on there if you want. I don't care about that. I'll give you one like that. I may try to ask you one or two more tricky questions about ARP based on you having done the homework. If you've done the homework, you'll be prepared for that. I may give you a table of ICMP stuff, ask you a question about that. I may give you a packet and give you a few ICMP tables and tell me, what do you think's going on? Who's trying to tell us something and what are they trying to tell us? So if you see, for example, the TTL is 0 and you see the message type is, exceeded your time, then you'll know, like, well, a router dropped this packet. And I'll probably give you that as multiple choice so we don't just go on this big giant fishing expedition, right? Like last time, right? Absolutely. Yeah, that's exactly right. I don't think I gave you another one before this, did I? Yeah, so it'll be just these two. I mean, we've covered a lot of stuff in lecture, but these are decent representative problems for what I expect you to leave those lectures, leave those chapters, and know how to do. Not a lot. ARP, most of the time, was spent trying to understand the whens and whys and hows, but the mechanics is what I'm looking for usually in these things. Can you spot an ARP packet? Can you spend a few minutes, go back to a book, pull up the types and codes, and within 5 minutes or less, figure out what's going on? I would be happy if I met you in 5 years and you could do that. Google for the table, look at it, and need a few minutes. I don't expect you to walk around Monterey with going like type 6, it's like it's like the thing you're seeing every morning, all right? Because I don't remember those after 45 years. So why would I expect you to do it? That's just memorization. I'm not big into that. So, okay. I'll expect you to know your way around the TCP and IP header diagrams. I gave you one of them here, but that previous problem requires, when I was asking you, like, how many, can you think of a address that's 16 bits? Can you think of a counter that's 4 bits? You're going to need to open up both of those headers. I will give them to you in the study guide, and I will give you guys a study guide like last time. So I'll put nice, pretty color things in there. I don't think it's important when you print it, but it occurs to me I might want to change this text to white, because I think if you print this in black and white, it's going to be like dark gray on black. Not so good. Okay, what else might I give you here? I may show you something in light mesh. That's really hard. I'm not super enthusiastic about being able to pull that off. But in cost, I will not ask you something more about cost. I will ask you something about, here's a network number, a host number, and something that causes you to have to design a little bit. I want you to understand that the network bits come first, the host bits are last, and what's in the middle are the subnet bits. And so this problem will test to see if you know that. I will give you a problem on converting base 256, so make sure you bring a calculator that knows how to do powers. And you might want to try to make sure if you type in 256 cubed, it doesn't say error or something like that. I don't think I'll ask you any more ands, ors, and nots. I will very likely ask you a question about this, but it'll probably be about the sequence numbers that we actually use in TCP. So does anybody remember the famous problem you have in TCP? And they went over it in excruciating detail last year in the book, but I don't know if anybody remembers it. It basically said, you decide that you have a sequence numbers of 0, 1, 2, and 3. You have 4 sequence numbers. So I have like 12 packets lined up ready to go. My window is the size of 4. So I'm going to send 4 at a time. So they gave us 2 scenarios. In the first scenario, you sent packet 0, it made it. Packet 1 got lost. You sent packet 2. You sent packet 3. Eventually, so this guy sends you back an acknowledgement for 0. He sends you back an acknowledgement for 2. He sends you back an acknowledgement for 3. What happens to your window over here? Your window basically moved over from 0 because it got that acknowledgement, but it's still wrapped around 1, 2, 3, and 0. And so it says, okay, I have permission now. I've slid my window over. I can send another 0. Right? So you can send another 0. Is the receiver going to get confused and think it's this one, or is he going to know it's this one? Well, you got an acknowledgement for 0, so it means he's also forgotten about it, and he's expecting to get these things. So when you send him another 0, the only one that's in his window is this one. He will correctly interpret the second 0 that you send as the second 0. So that's okay, that works. Where you get into big trouble, and this is why it makes a problem, is when the acts all get lost. So close to that. So I send 0, 1, 2, and 3. Right? All 4 are received correctly. 0, 1, 2, and 3. So my window slides over. And by the end of this, my window at the receiver looks like this. He's waiting on the second batch of 0, 1, 2, and 3. He's already forgotten. These are not the same packets. I'm just using sequence numbers over and over and over. I do that in IP as well. There's only 32 bits, so you do they just roll over every so often. So I don't get any acts back. They're all lost. So what's going to happen? What will TCP do? Yep, timer will go off, and you will resend the packets again. Packet numbers 0, 1, 2, and 3, correct? You'll send the first ones again. The receiver will believe you are sending the second ones. Why did this happen? What did I do wrong with the way I designed this that allowed this to take place? What do I need to change?
To the sender to say that I get your acknowledge.
Okay, so it would be nice if we didn't lose the acknowledgments, but I don't really have control over whether something in the future is going to get lost or not. Yeah. For sure, but what about the relationship between the window size and the number of sequences that I have? There's a really critical mistake in this design. Let me ask you this way. Was 4 different sequence numbers enough to not get confused about whether I'm receiving the first one again or the second one? I got confused, right? Because I reused 0, 1, 2, and 3 too soon. I need smaller windows or more sequence numbers. So in TCP, there's a really important rule they taught us last year in the book, which is you have to have at least twice as many sequence numbers as the biggest window you ever want to have. And you will avoid this problem completely, because if I had twice as many sequence numbers, these would be 4, 5, 6, and 7. And so when I resent 0, 1, 2, and 3, the receiver would just ignore them and resend the acknowledgments. Right? We learned that the hard way, like almost everything. You know, you just get hit in the head enough times and you figure out, like, okay, we need to change that. So 2 to the 32 is a really big number, but it does restrict you. It does restrict you. So something to keep in mind. All right. You guys must like this because I've already used 11 minutes for our next hour. So I promised you we'd leave at 8. Okay, there's a guy at WashU, and I really admired this question. Oh, I didn't drop this out on the drive for you guys. Let me put this out there real quick. TC2022, yeah. Share. All right, there they are. And I'm going to make them into, okay, it's out there. Oh, not quite. It's still syncing. And why is it taking so long? All right. Okay. I have finished uploading it to Dropbox. You guys may take a minute to pull it down. But let's start going through this. So anyway, I admired this problem a lot until I figured out it had some mistakes in it, which was unfortunate. But table below represents a forwarding table for IP. We've talked about all the pieces of this a bunch of times. So what I'm basically asking you to do is take a look at a few packets and figure out which line in this routing table it's going to match. So the first packet that we need to match is 1010-0110. So what are some candidate rows that might work? This one might work, right? Starts off the same. Is there another one that matches more of it? This one starts off the same, but this is not a match. This is a 1, and here I had a 0. Do I have any other candidates? I have a 1010. This one has a 0, but it has 2 zeros, and this one had a 01. Yeah, so this is the longest one that matches. Yes. Oh, thank you. Thank you. That could very well happen. Yep. Sure looks like it. Nice catch. Sorry. So here we go. You don't want to do last year's too? This year's is enough? Okay, thank you for catching that for me. All right, so I think for this one, the longest matching prefix was this second line. So the answer is port and address that you find over here. This address is the address of the next hop. So it's the next router, basically. Okay, does that one make sense? Let's do the next one. You guys walk me through this one. Here's the address, 0010-0110. What does it match? Okay, what else? Does it match any other rows? Is it big enough? Can you see it? Do I need to expand it a little more? It does match one other row, I think. Or does it? 0010. It doesn't even really match this because this isn't quite right. Is there a single row in here it matches? So what are you going to do with the router if you don't have an entry in your routing table for a particular network? Send it to the default route. Exactly. So this one will match the last row. Send it out port 9 to this router. Don't get too focused on whether these numbers make sense. Sometimes they won't. That's not the point of this exercise. That's the mistakes I found in his work. It didn't always match. All right. We ready to do the third one? The third one is 1010-0010. So I can paste it up here in red so that we can see it. 1010-0010. Does this match any of them? Matches this one and this one? All right. So the rule is you always pick the longest matching prefix. So which one's longer? The second one is. So your answer is here. So what does the hyphen mean? Why is there no next hop? Yeah, so this subnet is directly attached to the router. So either there's just a local LAN attached to the router port, or there's me and the other router, but maybe a few other devices as well. Whatever it is, I don't need the help of any more routers. I'm done with routers. I can see this device directly on port number 3. So I will just send it directly to them. So when I go to ARP, I'm going to notice that the MAC address that I get back actually belongs to the host that I'm trying to reach. And therefore I know I'm done. Right? Okay. We good? All right. So this is a different way of going about this. This is a type of tree that your router will try to build, but it's also hopefully a little bit fun. So what I'm basically asking you to do, and you can draw this however you like, I did mine, eventually did mine in, one of these drawing websites. I don't even know where I put it. It's over here. I drew it in that. You can do it in PowerPoint. Last year I got impatient and I just pulled out my tablet and drew it by hand, as you can see. But what I'm asking you to do is draw a routing tree to go with that table. So the way it works is, here is a pretend routing table, 0, 1, 1, 1, 1, 0, 1, 0, 1. So what I'm going to do is start drawing a tree. I'm going to pick which side is 1s and which side is 0s. So I have a 0, so I need this one. This leg I'm going to draw. I need a 1. Well, I've already drawn both of those, so that doesn't tell me anything. I need a 1, 1. So I'm going to have a second 1 here. I need a 1, 0. So I have 1 and then 0. So I'm going to need that in my tree. I have a 1, 0, 1. So I have a 1, 0. 1s are to the left, 0s are to the right. And I have a 1, 0, 0. 1, 0, 0. That's it. That's my tree for this routing table. Easy enough? So you want to try to draw the one for this one? For our table? This is one reason why you're very happy that they sort these things by shortest prefix first. So the first thing I need is a 1, and I need a second one after that. First row is finished. What's the second row going to look like? Do I start over here with the 0? Nope. So I follow the tree that I've got so far. I put a 0 here, and then another 1 and a 0, right? Okay. So I'm using, there's a network here, and there's a network here. That's it. Those are the only two places on this tree where there are networks right now. There's not one at every little junction along the way. So I could fill in the network number if I wanted to on these two places. I'm not going to do that. The next network I have is 0, 1, 1, 0, 0. Okay, 0, 1, 1, 0, 0. So I'm starting to be a little bit careful about these things not running into each other, but that's a terminal node as well. And then I have 1, 0, 1, 0, 1. Well, I have 1, 0, 1, 0. So I'm going to have another one here. And a terminal window here. Which one you want to do next? This one? What do I need for this one? Okay, I need a 0, 1. I need another 1 here. Oh, I have two 1s. There's one here and there's one here. So I have 0, 1, 1, 0. And I have a 0. What do I need to add? Yeah, that's what you guys were saying. Now I get it. All right. And that's a node there. 1, 0, 1, 0, 0, 0. Let's see if I can do that. 1, 0, 1, 0. We don't have this yet. 0, 0. So there's a node on my tree there. And then we're almost done, which is 0, 1, 0, 1. I have to add that, don't I? Oh, thank you. Thank you very much. I do. So 0, 1, 0. So this is where it's going to get hard to draw. So you may have to be a little bit careful. I don't care if you draw it like this. It makes no difference to me. But I know you guys, some of you are anal retentive enough that you will redraw the whole thing to make it pretty. Exactly like I would. So totally get it. Are there any of you out there? I know Anybody have more than 3 colors of pins in their bag with them right now? Yeah, so you're one of them. You test positive for that DNA trait. Yep, I have about 20 in my bag right now. You never know when you're going to need to really draw a detailed network diagrams. Okay, good. So that gets us through the tree. Wow, why am I asking the same question again? Forget this one. This is like the same one I asked before. Why? It looks like I copied. What is going on? I may have still posted the wrong one, guys. This is the same thing you've already seen. Yeah. So I need to throw a couple of these out because I already asked them to you on the previous homework, right? Yeah, I'm doing that now. But it doesn't matter. Just skip them. If you've already started typing into Word, just delete those. Just skip over them. Because this is going to work. When you turn it in, you get 100. So I'm not going to grade it. I just expect you to keep up and understand the concepts. Ask questions here and now. This is our last lecture before the test. So this one I'm not going to bother grading. It'll be just like last time. Okay. We've add this, and now I think we have another new problem. Okay, so here's the network diagram. This one's a little harder. So what I'm going to do is, I think what I want to copy over is the diagram, not the table. Let's see if I'm right about that. So I have a left router, a right router, and a middle router. So left, right, and middle. So what I'm asking you in this problem is fill out the rows of the middle table. So it's a little bit harder, only because it's a little bit tedious. So let's dive in and see if we can figure it out. So the first thing I'm asking you is if you're at the middle router, which is this router right here, and you receive a packet and the destination is to, you have an entry in your routing table that matches this IP address 1220/29, where will you go to reach it? Well, I see all of my 122s are up here, but there's 2 different LANs. One of them is on port number 1, one of them is on port number 2. And here are the IP addresses of those ports in case anyone cares. But I got to figure out if I'm looking for 1220/29, am I talking about an address here or an address here? Well, I haven't really told you everything about these subnets. I haven't told you the subnet masks of them, but this is a huge hint. It's a /29. So let's try writing this thing out, 1.2.2, and the 29th bit is going to be in the last part, correct? 25, 26, 27, 28, 29, 30, 31, 32. All right, let's just go pick an address on each LAN and see which one could possibly work with this subnet scheme. So you want to do the left side or the right side first? Do the left. All right. What is 9 in binary? 1001. All right. With this subnet mask, do I have permission to change this bit? No. The network manager does, but I only was given permission to change Z3. So 9 could not be represented in 1.2.2.0/29. It's impossible. So it can't be this side. What about 2? What's 2 in binary? 10? That'll fit. I only need to change the 3 bits that I can in order to represent the numbers that I see. So it must be that this subnet number is talking about this LAN that I just circled. So where should this middle router send a packet that matches that prefix? He should send it over port 2. So I can add a 2 in here. And what is the next hop IP address? Do I need another router to get it here? No, I don't. So the next hop is blank or hyphen. I see why you said this, because it's the address of this port. Don't get fooled by that. I don't need his help. I'm already inside this router. I don't need to send anything. If I send something here, it'll just come right back inside again. I'm trying to get rid of this thing. All right, make sense? All right, let's do the next row. 1210/24. Okay, here's 1, 2, 1s. All seem to be here. There's a couple of subnets here, but there's really no need in worrying about whether it's this LAN or this LAN. Why?
Because you first need to send stuff.
Exactly. That's his problem. It's the right-hand router's problem, not mine. I can't see those LANs. All I know is that all of the 121s are over behind this guy. Therefore, if I get a packet for a 121, I look carefully to make sure there's no other exceptions. I need to send it to this router. Which port will I use to reach this router? I won't use 1. She said 3. How many people think it's 3? Stop. Don't do that. Stop. Stick with your answers. Have confidence.
No, I want to explain.
Okay, good. I thought you were backing off from it. Don't do. All right, let's listen to her argue for it.
Because it says we are the middle router,
Mhm.
so I think we are the working, so we only have 3 ports,
Yeah,
the 1, 2, and 3.
right.
So if we want to send something, we need to send to the 3 to get to that.
Done? Exactly. Nailed it. But did anybody else say 3? One other person to it, kind of? All right. So yeah, there has the easy thing to do is to guess, I need to go to where I'm going. Yeah, you do need to put an address over here, but you got to leave your router out of port number 3. Very good. And makes me very happy. And what is the next hop IP address? Now here's where what's going on at this port is going to come in important. What IP address does that port have? Yeah, right here. This one. That is your next hop IP address. You can see that port. There's a LAN in here. Just to make sure you guys still remember how this works. There's a LAN working over here. I need a little more yellow. There's a LAN right here. Right? That's a LAN. It has the 3 routers and the server on it. So the only thing I can see are the hardware addresses on this LAN. I'm going to ARP to figure out what the hardware address is associated with this, and I'm going to get back the hardware address of port number 1. But in order to make that happen, I've got to send it out of port 3. That gets it onto the yellow LAN. When I stick it out port 3, I'm now on the yellow LAN. And when ARP goes out, it's going to go here and here and here. And this guy's going to answer with this hardware address because he has that IP. Make sense? Okay, this is not a question about ARP, but I'm just going to try to reinforce that for you. 1, 2, 5, 1. Okay, let's see if we can do the next one maybe a little faster without me interrupting her in the middle of a perfect answer. All right, so 1250/24. Where are the 1250s? Well, where are all the 125s? Yeah, it's that yellow LAN I just drew. How convenient. So what port am I going to use to reach the devices on that? And what's the next hop IP address? So there's routers on this LAN, but it's also this LAN. Do I need any other routers to route? No. All of the 125s are here. Yeah, so it's another tricky one. So it's another bravo. Yes.
Then
Because in order to reach this LAN in yellow, you must drop the packet out the port that belongs to that LAN. The only one of your 3 ports that can see this LAN is this port right here. So if you want to get your packet onto this yellow LAN so that it could reach, say, here, or here, or here, the only way to do that is out port 3. If you go out port 1, the only place you're ever going to get to out of port 1 is this LAN. Yeah, this is a table for the middle router. Exactly. Yeah, is that what you're missing? Okay. All right, 1230. Finally, another easy one. Where is LAN for 1230? Yeah, it's actually both of these ports. I don't know where the 0 is. I don't care. What this means is that this router is advertising that he can help you reach, and what he really can help you reach is 1.2.3.0/29, and he can help you reach 1.2.3.8/29, but he doesn't need to advertise both of those things. He can actually advertise 1.2.3.0/ less than that. He could advertise it as a 28. He chose to advertise it as a 24. That tells me he's got a lot more LAN here than he's showing me. But that's okay. It's the only thing that looks remotely like 123. So I'm going to send it out port 3 to this IP address. Right? Make sense? And then for the last one, 1228/29. So now we're 1228. Where's the 122s? We finally finished. Remember, we started off up here first, and we couldn't do the 9. Now we can. Because if I'm doing 122.8.29, that network looks a little different than this blue one. Here's how it looks. It looks 1.2.2.00001, and then I have 3 bits I can play with. What's 9 in binary? 1001. How convenient. This 1 is already set for me. So I can represent numbers that start with 8 and go to 15. Port 1 and no IP, no next hop. Does anybody need me to go over any other part of this? To help you out, there's 2 more tables in the homework, one for the left router and one for the right router, and they're already done for you. So if you want a little more practice, go look at the left router and see if you agree why these port numbers and these next hops are what the left router would have in order to reach these networks. So let's just pick one. If I'm on the left router and I want to reach 1250/24, 1250 is this yellow LAN. I will send it out of port 2 and no next hop, and that's exactly what I have. So you can use these to practice more if you want. How are we doing? That makes sense? Did you have another question? I changed the table, yeah. I'm just pointing out there's 2 other tables here if you want. All right, how many addresses are in the subnet assigned to the LAN with 1232? Well, let's go find 1232. It's right here. And it looks like it starts at, like it includes a 1 and a 2. And 8 is over here. It's separate. So my guess is that this is 0 through 7. 7's the broadcast, 0's the network number. My guess is that this is a /29, and it's got 8 addresses on it. What IP addresses on this subnet are still available to be assigned? She just said something really important. A broadcast address is on here. So if it's a /29, we already know from before I have 3 addresses to play with. Here they are, or 3 bits to play with. The combinations are this. This is my broadcast address. That cannot be assigned. This is my network number. That cannot be assigned. Furthermore, I can just look and I see that I've already assigned .1 and .2 to other devices. How many addresses are left? There's 4 that haven't been assigned, and they are, what is this number in decimal? 3, 4, 5, and this one would be 6, I guess. Do you see that in here? 3, 4, I don't know why it's quite worded this way, but it's this one. And this should basically say 1.2.3.3 through, but hopefully you guys knew what I was trying to say. I kind of typoed it a little bit. So I would totally brute force it. I would just write them out and draw lines through them and count which ones are left. Because I'm assuming, and it can be dangerous, but I'm assuming that the subnet that includes 1 and 2 but does not include 8 probably starts at 0 and goes to 7. But it could be dangerous because it could start at 0 and go to 3. It could be a /30 instead. I would accept that also as an answer. If you told me that there were only 4 and then you gave me the answer for that here, like 1 and 2, then I would accept it. But in that case, the answer would be none. .0 is the network, .3 is the broadcast, 1 and 2 are already done. If you answered it that way, I would have counted the answer correct. Right, so don't freak out over something like that. If you interpreted the question correctly, I will grade it correctly. It does not matter whether it matches my answer key or not. What matters is if I see that you understand how to do the problem. And what you just asked suggests to me you see the second way of doing it. That's great. That would be counted as correct. Right? That's far more important than getting the answer that one answer that I got. There's very often more than one answer to these things. Very, very often. So I just gave up. People ask, like, why don't you use Scantrons? And I go, like, why don't you know networks? You can't test networks that way. It doesn't, at least not any way I've learned. All right, so here's one last diagram here from the book, and I've got it in the book a little bigger. Salud. Are those coughs or sneezes? I'm not sure. Okay, salud then. So I come back over here. I actually think I had this in here at the beginning of class. Yeah, I did. Okay. So I'd already pasted this in, so it'd be a little bit bigger for us. This will make it easier to see. Okay. The questions on this one are, a packet arrives at the router with the destination address 145.14.192.71. How is it forwarded? 145.14.192.71. All right, the first thing I should do, where should I go? How are you going to solve this problem? Try checking the routing table, right? First you go find it, see if it's there. So I have a bunch of 145.14s. This is 192, so there is an entry for that. Doesn't show me the subnet mask, which makes me upset at the author, but this is the book's diagram, not mine, right? So I believe that this one, if I can get back, find it down here. I believe that this one is probably, this takes 4 bits, so I think this one's a /26. I think they're all /26s. Because if I look at these binary values, 0 is this, 64 is this, 128 is this, and 192 is this. 2 bits. 24 up to here, 27, 28, 25, 26 rather. I think these are 26s. This told me it was a /16. So, oh, actually, these are in the 3rd tuple, not the 4th tuple. So /26 isn't correct. It's just 2 bits past the 16. So these should be 18s. They told me they only went up to 16 bits, and that's right. It's still 2 bits, but it's in the third collection of them, not the fourth collection. Okay, so I've got 145, 14, 192. I have the remaining 32 minus 18 bits left, which is another 16 bits. Yep, 14. All right, yeah, I didn't quite explain that very well either, so fair enough. I'm given a /16. /16 means the first 8 bits are going to be the same. They're given to me, and the next 8 bits are the same. After that, I have, it just turns out, I have the remaining 32 minus 16 bits left, and here they are. Okay, then it looks like I've broken this up into 4 blocks. 1, 2, 3, and 4. Well, we count in binary, so maybe I should count this 0, 1, 2, and 3. So let's go figure out sort of how I decide what's going on here. And they have mistakes in these diagrams, so we're going to have to sort that out. But because I'm going to go into it in detail, I'm going to uncover one of them. So the first one, let's go with the lowest numbered one here. How would I, if this was this router port's address, which is where this is supposed to be, not next to the switch, it's telling me it has 145.14, 0, and then a .1. Well, how would I draw the 0? Well, it's the part of the third one here. It's the same. It's what I've already got. I don't need to draw it again. So the last part down here is going to be a 1. All right, so that's the first block. What about the next highest number? It's this one here, 64. How do you draw 64 in binary, starting with the 17th bit? Because the 16th bits are, first 16 are stuck. That's a /16. So how would I draw 64? How would I write it down? 64 is 0, 1, 0, 0, 0, 0, 0, 0. Okay, what about the next one? This should be a 128. That's the mistake. Right? So the 128 is actually, this should be, it's the other one. This one should be the, yeah, this should be the 128. So they tell us it's a 128 here. 128 is written like this. And the last one is a 192. And I see that here. So 192 is written with a 64 and a 128. So what do I notice about these? These are all able to be written with bits 17 and 18. So if I'm going to divide this up into 4 blocks, this is probably exactly how I would have done it. I would have taken 2 more bits to get me 4 combinations. The first group will have 0, 0. So he can have addresses in this block. They're all going to start with 0, 0. And then the remaining 6 bits can be zeros all the way up to 6 ones. What is the value of 6 ones in binary? Well, it's 1 less than the value of a 7th one to 0. It's 127. Because if this, you add 1 to this, you get 1 and zeros, and that's 128. So my valid range of IP addresses for this first block over here are going to be 145.14.0.0 up to 145.14.127.255. If I set all of these to 1s and the last 8 to 1s, that's the decimal number I'm going to get. This 127 keeps the leading 2 bits as zeros, so it can stay in this group. The next group has this set, so he can have addresses in the range of 145.14. What is this value here? Yeah, 64.0. That's his first IP address in this block. And the last IP address in this block is going to be 145.14. Well, whatever the heck, 0, 1, and then 6 more 1s. What's that number? Well, what's 1 more than that? Nope, not quite. Close. What was this third one here? Right, so this is 192, so this one should go up to 191. This one should go up to 127, because this number here is 128. and this is 192. So if I start off a number with 145.14 and then a 0 and a 1, and then I figure out what are all the combinations of the bits that I get to change in my LAN, it's going to be these 6 bits, and they're going to go from all zeros to all ones. Well, the all zero one is easy. It's the same number, but the all ones is 127.255. That's the number you get when you start off a number with 145.14.01 and then all zeros all the way up to all ones. That's what you get. The last one will range from 192 to 255. And so long answer for how I got 18. You could also look down here and maybe you can see some hints in here as well. Yep. Oh, it can't. It can't. I did write that down. What should it be? Yeah, 63. Thanks for catching that. So let's do one more to make sure I don't blow everybody up here. All right. Let's say I have an address that looks like this. And I tell you the dividing line is here. I have no idea what slash it is. I don't care. If you want to figure out what your total range of IP addresses are, you set all of these to zeros because you get to play with all these bits. They told you this was a slash. Everything after that belongs to you. And you figure out what this is in binary. Well, it's 0 and decimal. And then you go all the way up to where they're all ones. You get all the combinations in between. And this up here is one of those combinations. But it wasn't important to figuring out the total. So I took the slash, zeros to all ones. You just figure out what this number is in binary, and that's what it is. So if this belongs in the middle of a string, which it does here, it belonged in the middle of this block. When you want to tell me what the range of IP addresses are I get to use, here's how you do it. This one isn't going to change. That part, you're set. You're fine. The problem is the second one. It's also not going to change the third one or the fourth one. So I know the third one's going to range from 0 to 255, and the fourth one is going to range from 0 to 255 because I have all of those bits in both of those. My problem is here because the first 3 bits have been set, and that's going to make it hard to do the math. So I have the first 3 bits, and they are set to 110. So my first address is going to start with these 3 bits as 110, and my last address is going to start with these 3 bits as 110. They're part of what I was told I can't change. So what can I change in here then? I can change the last 5 bits, 0, 0, 0, 0, 0, up to 1, 1, 1, 1, 1. What is this number? You're going to have a table to look it up, or you can just observe that it's 192. And then what's this number? Well, it would be 255 if I hadn't taken out the 32 out of the middle. So what's 255 minus 32? 223 or 233? 223. Right, so 223. So what that means is my range of IP addresses on this network that I can tell my router, you can hand out these following addresses. It's going to start with whatever this is, .192.0.0, and it's going to go up to whatever this number is, .223.255.255. This is my network number. This is my broadcast address. So I'll reserve those 2, and everything else in between I can assign. All right? So back over to our problem as we kind of... You have to be told the location of the slash. Yeah. Yep. So I kind of guessed it to start this one off before I remembered, oh, it's right down here. It's actually written down for me. It won't be always. You can make a judicious guess. I'll go, good. I'll take it. Guess is fine as long as it's not, you know, can't work. If it can work, then I'm okay with that. All right, so back up to our question, 145, 14, 192, 71. That seems to be well within this range. What is 71, though? Let's check. How do you write down the number 71? Does anybody know in binary? It doesn't have a 128. It does have a 64. Yep, plus 4, plus 2, plus 1. Okay. Is there any reason why in a /18 network that I cannot write down 145, 14, 192 dots this? Where do these 8 bits sit to make it a 71? Well, they told us it was in the last tuple. So this network is a /18. The dividing line happens in here somewhere. I get all 8 of these bits. This is no problem. I can represent 0 through 255. So that's perfectly fine. I will send this packet, therefore, to this subnet on port M1. But I don't have another hop, so my next hop IP is blank. I don't need the help of another router to get there. All right, let's look at the next one. Yes. Port M1. Because 71 is in this range here. In the one that I just drew the box around, in the range of 145.14.64-0 up to 191.255. No, 127.255. If you're not sure, then go back and look at this. Oh, that's wrong. I thought it was a 64. I'm sorry, guys. I had it covered up. I forgot. It's a 192, right? So that's why you're asking me. So where is 192 in this? It's actually this one, correct? Is that right? Did I get it right this time? All right, so it's 192. So which port should it go out over? Yeah, it should go out over M3. I'm going to look at it again. Do I still have it right? Okay, good. Yeah. Looking at too many numbers. I forgot. I need to shrink my window a little bit. Okay, let's do another one. I have a destination address that I don't even recognize anywhere in my table. Immediately send it to the default route. Done. This one's going to go out port M4. And I have no idea what the next hop address is, but there is one. So I'll just write text in here that says something like the ISP's router or something like that. Because it's not blank, but they didn't tell me what it was in this diagram from the book. I would have written in what it was. All right. And
in the past one, the next hop IP
it's in the last one, it's blank because you don't need to go through any other routers to reach this LAN. It's directly connected to you. Right? Okay, next one is how many addresses are available in each of the 4 gray box LANs? Well, how many addresses are available? It's a /18 in each of these boxes. So that's the network plus subnet mask. How many addresses are left for me to play with? 32 minus 18, which is 14. 2 to the 14th, that's the answer, 14. And then the last one on this one here, oh, it's not quite the last. The overall block is a /16. Have they assigned all of the available addresses to the gray LANs? Not are there 2 to the whatever host, but have they divided everything up? Are there any big blocks that they have not assigned out to one of these gray boxes that they're still holding back? She says no. But of course she's closer to me, so I hear everything she says. So maybe other people are saying no too.
No, because they use the 4 bit.
Yep. They used all the combinations
All
of
the
bits
2 bits.
17 and 18. This one's 17 and 18 bit is 0, 0. This one is 0, 1. This 17 and 18 bit is 1, 0.
No,
I got it
that's
backwards.
not the one.
Thank you. And 1, 0. So I don't think I see any big blocks left. You know, if I saw 0, 0, 0, 1, 1, 0, but then I didn't see any of the boxes that had 1, 1, then I would go, yeah, you haven't assigned them all. So I don't think so. I think that's a no. If you change the site block to a /15, how many more or less gray 18 lands could you assign? All right. Okay, so one person's given an answer immediately. Right now I have a what? A /16? Is that right? I have a 16 so far. And when I made my subnets 18, now you see why I had you work backwards on that other homework problem? So I have 16 up to here. They're everything from 18 on, which is 14 more bits, is over here. It left me with 2 bits in the middle, correct? The 17th and 18th bit. And that gave me 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And now I'm telling you, back this up one more, make it a /15. This guy is going to grow out 1 more bit. Now he's going to be 3 bits in size, not 2 bits. How many combinations can you have of 3 bits? 2 to the 3rd equals 8. You had 4 combinations before. Now you have 8. So how many more /18s have you added? 4 more, from 0, 0, 0 to 1, 1, 1. And your 0, 0, 0, 1, 1, 0, 1, 1 are the first 4. And then you do the same thing with 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. That's the last 4. So 4 more. All right, 4 more. And then we're done. Routing table. This is exactly the same problem again. No, not quite. So what you need to be careful of on the exam, this one's very similar to the other one. You need to be careful that I give you a problem. I'm going to tell you exactly what I'm going to do to you. So you need to be able to watch for this. I'm going to give you a problem that says you have an entry in your routing table that looks like this: 128.249.192.0/20. And I'm also going to have a default route somewhere else. And then I'm going to say, all right, an IP address is shown up, and it has the address of 128.249. It's got a destination it's trying to reach. Here is the IP destination address, and it's going to be something like 223.14. And I'm going to ask you, which route in the routing table do you use? Your first inclination might be to say this one, but do you know how to show that it won't work? Here's how you do it. You take the first number that you were given and convert the tuple to binary where the division is. Where is /20? It occurs somewhere in here, right? All right, so let's break this one up into binary. What is 192 in binary? 1100, 0000, and then we'll go back to decimal again. So where's the 20? The 20 is right here, correct? So let's see if this address will fit. The address I've been given is 128. Well, that matches okay. 249, that's fine. Here's my question, because here's where the slash is. What's 223 in binary? It's at least 192 plus 31. Is that right? Okay, so how do I write 31 in binary? 5 ones. So this is going to be a 0, and this is going to be a 1, 2, 3, 4, 5. Does that match this? It requires that I change one of the bits to a 1 that cannot be changed to a 1. This number, 128.249.223.14, does not belong to this subnet. It does not belong to this subnet. It can't. So just be careful, be able to kind of bust one of these things out. Correct. You'd be fine. Yep, if you'd have been a 19, then the only ones I would have been forcing you to keep the same were these first three, and this would have been part of what you could have changed, and you did, I would have been okay with that. If it had been a /19, you wouldn't have had this problem. All right, guys, I will give you a study guide. I will release the solutions to this one. I can probably do it now because we're just going to go over it together in the other two sections as well. It doesn't hurt anything to give these out. So I can do that so you can start studying this one. The other one's due Thursday night. So wrap that one up. Use chat. Make sure you guys understand it. I'll give you a study guide. Maybe I made this one originally due Saturday night, but it's irrelevant. I'm going to give you the solutions for it now. If you turn it in, you get 100. So just turn it in. Don't turn it in blank, please. Don't try my patience. But you know, turn it in. I don't care if you do all of one. If you see what's going on, you draw the tree and you just say, etc. I'm okay with that. If you are comfortable, you know how to do the rest of it, just say, I got this, and I'm okay. That'll count. Right? If you want the practice, then work it out in detail. It's there for you. Yes, sir.
You have to answer the last question.
This one, no, because we didn't get to it. So it's no longer part of the homework. It will not be on the exam. That's exactly right. So this homework got a whole lot shorter. So what I'm going to do is save it back out again. And before I walk out of the room, put it back out there for you guys. You might want to check to make sure I don't put last year's out there again. Yeah, it'll take a few hours for WebEx, so it might be in the morning, but because it takes 1.5 times the length of the lecture before it produces the MP4 file, and that's like 10 p.m. and I'll be up probably, but you know, no guarantees. Okay, let's see. I printed it out, but it printed it out to the wrong folder. So let's print it out here. All right. Do you like the way of prepping for exams and kind of plowing through this stuff? Does this work for you guys? Okay. All right, they are now updated and re-uploading to Dropbox. Okay, what else do I need to do? I need to drag the solutions over there, but I need to throw a lot of these out because the solutions aren't the same anymore. All right, I think we're done, right? Okay, we good? Happy? See smiles. You feel like you can do this? You kind of getting more and more concepts down? Okay. And networking is a little different sometimes than anything else in computer science. It's not coding exactly, so. All right, I'm going to end the meeting then.